Okay, can you start?
Yeah.
Good afternoon, all. Welcome to the weekly online course on radar meteorology organized by South Asian Meteorological Association and Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. Today we have the 18th lecture of this online course. Today we have Dr. T. Narayana Rao from NARL as a presenter. He is taking his second lecture on the topic Introduction to Dual Polarization Radars, Inferring Microphysics from Polarimetric Parameters. Before the start of the lecture, I invite Dr. Devapradhan sir for the Chairman Advisory Panel to give the welcome address.
Thank you, Rakeshji. At the outset of this today's presentation, I would like to give my sincere thanks to two strong pillars of this summit, Professor Ajit Tyagi sir, Professor Someshwar Dayas ji, and the supporting management, the other honorable members. So I welcome them first all, Dr. T.N. Rao, who is delivering today the second lecture. Today I got this opportunity to welcome my friend Dr. T. Narayana Rao, who is one of my old friends when we worked together in many conferences and many projects, and I know his capabilities, that he is a very good researcher and very good person technically, principally, and research also. So it's a big opportunity that uh, after attending this lot of what should I say, experience. So he is with us, and after the introduction of this single polarization radar, now he is switching over to the dual polarization radar. And here I would like to say to all the participants that the most important thing about the dual polarization radar is that it carries the properties of both dual single polarization. All the basic variables, parameters are available. The products are available. In addition to some special parameters are also available with the dual polarization, which help them, the forecasters, in nowcasting as well as in research also. So today he is going to focus on dual polarization radar and its applications in the research nowcasting. So I hope that this lecture will be the one of the most useful lectures, because it will show its superiority over the single polarization radar. So it has got both horizontal and vertical polarization, as we know. So it is a if the people can understand it very well, along with its applications in day-to-day life, the forecasting, that is, I should say, the basically nowcasting, and especially the prediction of the health and other things can be done very well here. So this lecture, I feel that it is one of the most useful after the introduction of the single polarization radars here. So once again, my sincere thanks to Dr. T. Narayana Rao, and I invite him and just to deliver the lecture to enlighten us regarding the dual polarization, because I'm also slightly weak in understanding the second dual polarization, because it is more based on the practical experience. More you see the images and the data analysis, more you will be getting the perfection here. So finally, I give my sincere thanks to each one of you who have contributed a lot, and I request Dr. T. Narayana Rao to deliver his lecture after the lecture speech by Professor Ajit Tyagi. Thank you, everyone. Thank you, Dr. Rao.
Thank you, Pradhan sir, for the welcome address. Now I invite AVM retired Professor Adityagi sir, President of SAMA, to give the presidential address.
Thank you, Rakesh, and I join Dr. Pradhan welcoming our distinguished speakers for today's lecture, Dr. Narayana Rao. He has been kind enough to deliver the second lecture, and with the passage of our series of lectures, I think now the participants are in a better position to appreciate the application of radars, both single and now the dual polar radars, and therefore this lecture is rightly planned in a way that the advanced application of the dual pole radars is put across to the participants to make use of it. We all know about Dr. Narayana Rao, and he's from the institutions NARL, where right from the boundary layer radar to the MST radar to even to talking about the space-based radar are being, I think, operational, as well as the research is going on that. So there's a big knowledge center of as far as the radar meteorology is concerned, and there couldn't have been a better speaker than the Narayana Rao to deliver it. And I'm happy that today's lecture is also going to be a landmark in the field of the radar meteorology for the application part. I'm thankful to many of our distinguished ECT members, and also Dr. Wu from the Myanmar, Mohan Kumar from Bangladesh, and of course our other ECT members, Dr. Mili and others who have contributed. And I'm happy about the, you said that they have got a backup in Rakesh also to organize this meeting. So that's great and uninterrupted and very supported by entire CUSAT team. So thank you so much, Rakesh, and all the best. Thank you.
Thank you, sir, for the presidential address. So we have already introduced T.N. Rao sir previously, so there's no need of another introduction. So now I invite Dr. T.N. Rao sir from NARL to take the lecture. Welcome, sir.
Yeah, thank you. So you're able to see my screen?
Yes, sir. Yes, it's visible.
Yeah, okay, thank you. Thank you, Tyagi ji, Pradhan ji, and Rakesh for introducing me to the audience. Today, actually, you have been hearing about the single polarization radar from the last 14 weeks or so. And then the fundamentals of the single polarization radar, and then the applications of this radar, and then in both operational applications as well as research applications, and then assimilation of the single polarization radar data, particularly the reflectivity and the Doppler velocity. So we know that actually the applications of the single polarization radar, and it's a very useful tool to understand the processes in the atmosphere, particularly the related to the weather, related to the rain and clouds. So today I'm going to talk about the polarimetric Doppler weather radars. Just I'll introduce this polarimetric Doppler weather radars, and I will also talk about the microphysical interpretation of the polarimetric weather radar products. So this is the outline of my presentation. First, I will talk about what are the problems with single polarization radars, what are the error sources that actually triggered the dual polarization radars, the development of the dual polarization radars, and then I will talk about some fundamentals of dual polarization radars, and then what kind of products it will give, and then how we utilize those products for improving the quantitative precipitation estimates. And then also how we will infer the microphysical characteristics of precipitation using those parameters. And then also for drop side distribution, is very important fundamental property of the rainfall, and it's being used at it is having several applications. So how do we derive the drop side distribution using the polarimetric radars? And then if time permits, I will also just briefly tell about the how do we classify different types of hydrometeors. We all know that actually the single polarization radars, scanning weather radars, actually have a lot of applications, particularly in estimating the rainfall over a large region, something like something like with the radius of 100 kilometers, 120 kilometers, you will get rainfall over that region. And then also we are extensively using this Doppler weather radar, single polarization Doppler weather radars for tracking the storms. So these are the two basic applications, and also of course radars provides the vertical structure of precipitation, which probably this is the only instrument which will do that kind of vertical structure. So we have been hearing about this single polarization radar for the last 14 weeks. And then of course this slide I borrowed from Dr. Suresh. So several applications he has listed for estimating the rainfall, for estimating the wind shear and turbulence, then the gust fronts, genesis of convective storms, several things, then track and movement of storms. So the applications is having so many applications. But then at the same time, the single polarization radars also suffers with several errors. So this slide I just took from the WMO Guide to Meteorological Instruments and Methods of Observation, and you can see several error sources are listed there. Then I just some of them I have listed here. The major error sources. One is the drop shape. You all know that actually once the drop is when a drop is small, then it looks like a spear. But then as the drop size increases, it differs from its sphericity, so it becomes like a spheroid, blade spheroid. So then in that case, if you're using a single polarization radar, for example, a horizontal polarization radar, then the scattering cross section will increase. For a horizontal polarization radar, you get a strong reflectivity because of that. And then you use that the strong reflectivity, and if you convert into rainfall rate, you will overestimate the rainfall. And if you are using a vertical polarization radar, you will underestimate the same reason you will underestimate the rainfall rate. So the drop shape it's a natural process. It's a drop shape because of the deformation from its sphericity that will cause some error in the estimation of rainfall. And then and then on the right hand side, you see how the drop size changes as the shape increases. There are different models actually people have proposed based on some data, and then laboratory data and also the real data. At least 6-7 models are very famous. How they drop the axis ratio, the major axis, minor axis to the major axis ratio changes as the drop with the drop size. It decreases as you see here, and the drop size increases. The ratio is becoming less than 1, indicating that it is differing from its sphericity. The other problem is actually the conversion of reflectivity into rain rate. So I will just show one slide and then I'll come back again. You see this slide, because radar gives only the reflectivity, but then the common man wants the rainfall. So we need to convert the reflectivity into rainfall using some empirical relation. So this slide, this figure I have taken from Batten in one book written by Batten. It was published in 1973. And then you see that by that time, how many relations are there to convert reflectivity into rainfall. And then you can also see the famous Marshall-Palmer relation, Z is equal to 200 R to the power of 1.6 in the middle of that distribution. This is in 1973. By now, I think several thousands of relations are available now at different locations. Giving for Jada relations are available now. So this is which one we have to use. So which one will give the correct rainfall rate? So that is a big question. So then people have talked about then because this Jada relation changes with the region, from one region to the other region, and also changes from one rain system to the other rain system. So there is a big puzzle how to which one we have to use to convert to get the correct rain rate. And if you are using a high frequency radars, then attenuation if you want to attenuation by rain, it becomes a major source of uncertainty, because you want to estimate the rainfall rate and then rain itself will attenuate your signal. So you need to correct for attenuation. But how do we correct? There are different methods people have proposed, but still some uncertainty will remain in the estimation of attenuation, and then which will cause the error in the rainfall estimation. and then some other changes, some other error sources are there, because with a radar you are measuring the rainfall at some height, and then the rainfall will not fall with the same rain rate, because as it comes down from that height to the ground, there are several microphysical processes occurs, and then it will change. So this also will cause some error in the rainfall rate at the surface. Then because hello, yeah,
sir, please hide that share screen.
pardon?
That in the downside, some labels are there, sir. Can you please hide that one? Stop sharing right there in the screen. That. Okay.
Is it
Thank
okay?
you, yes, yes,
Okay. So the radar basically gives only the reflectivity. Single polarization radar basically gives only the reflectivity factor, only one parameter for calculation of rainfall. And so we need to calibrate the radar correctly, then only you will get the reflectivity correctly. So accurate calibration of the radar becomes very, very important. Otherwise, it will create an error in the reflectivity, and then that will propagate into the rainfall rate. And then with single polarization radar, it is difficult to identify the non-meteorological targets like birds and other things. So that will also cause some error, particularly when you're estimating rainfall. So these are some of the error sources, important error sources, which we need to tackle. Of course, there are other error sources like we talked about, the attenuation by gases, clouds, rain. So anyway, we'll discuss these things a little later. So to account these problems, or to address these problems, to overcome these problems rather, people have proposed the dual polarization radars. So the dual polarization, that what you are doing is you are transmitting with the two polarizations, one horizontal, typically one horizontal polarization, one vertical polarization, so that you will get echoes from both with both the polarizations, and then you can actually characterize the rainfall, and you can estimate the rainfall in a better way with a dual polarization radar. So in addition to the with a single polarization radar, typically you get only the reflectivity, the Doppler velocity and spectral, the three basic moments you will get, the parameters you will get, and then from those three basic parameters we will estimate different atmospheric variables. But with a dual polarization radar, all three you will get it with the two polarizations. So, and then in addition to that, several other parameters we can derive, and those parameters will be very, very useful in improving the rainfall estimation, and also in understanding the microphysics of precipitation. For example, on the bottom right, I have shown that if you are transmitting horizontal polarization, you can receive with horizontal polarization and also with vertical polarization. So you can get, if your radar is capable enough, then you can get both the backscattered echoes, and then you can calculate the backscattered powers from, if you transmit with one polarization, and you can receive with two polarizations. Similarly, you transmit with other polarization, say vertical, and then you can receive with vertical, as well as you can also receive horizontal polarization if the target is a depolarized, is having the capability of depolarization. So you will get all four components, four matrix, you will get four powers, and from there you will calculate several other parameters. See, for example, these are the basic polarimetric parameters, scattering parameters that you get. So one is called the differential reflectivity. So what is differential reflectivity? Is the ratio between the horizontal and vertical polarization, polarized backscattered signals. So so as I have shown before, so when you are transmitting with horizontal polarization, you can get in the same polarization, you can get the backscatter also. So that you can convert that into the reflectivity for horizontal polarization. Similarly, you can also calculate the reflectivity for vertical polarization. The ratio of these two will give the differential reflectivity. So which is actually a good indicator of drop shape. So we can quantitatively tell that if the the differential reflectivity is greater than 1, then we can say it is an oblate shaped spheroid. and if it is less than 1, then we can say it's a prolate shaped spheroid. And then if it is 1, then we will get it. We can say that it's a spherical raindrop shape. Okay, so it is actually we can get the shape of the raindrop, so it's a good indicator for that. And then also later we will see that actually we will also estimate the median volume diameter using this parameter ZDR. And then there is a correlation coefficient. So because you are transmitting pulses with horizontal polarization and also with vertical polarization, so you get a time series of backscattered signals. So those two, if you correlate, then you will get the cross correlation coefficient. So this is a good indicator for mixture of precipitation types. For example, in the melting region, the melting layer or radar breadband region, you will have a mix of both the rain and then snow. So that you can easily identify with the correlation coefficient. And also it is very useful. So this is a correlation coefficient. This is very useful for identifying non-meteorological targets. And also the linear depolarization ratio. This is what V by H power returns from an H pulse. Suppose if you are transmitting with the horizontal polarization pulse, if you are transmitting, then the cross polarized signal, also cross polarized signal to the copolarized signal, the ratio between these two will give the linear depolarization ratio. This is also good, is a good indicator of mixture of precipitation types. Those are from the backscattered power, you can calculate those parameters. And also there are from the propagation effects also we can calculate some parameters. For example, if in a normal, suppose if you are transmitting two polarized two polarized signals like horizontal polarization and vertical polarization, in a vacuum normally you don't see any change in their speed. But for example, if suppose if they travel through a medium of consisting of raindrops, so the raindrops are spherical in nature. So what happens is then the speed will be the propagation speed will remain same for horizontal and vertical polarization. But assume that if there is an oblate shaped raindrops are present, then then there will be a differential phase will come because of the propagation phase. The speed will be different for horizontal and vertical polarization, so that you will get some differential phase. So that also will give some other parameters. So the propagation effects will give some polarimetric products. For example, the differential phase, that is the phase difference between the horizontal and vertical polarization signal. So from there you can calculate a parameter called specific differential phase. It's a range derivative of the differential phase. So which is a very, very important parameter in polarimetric radars, for polarimetric radar research. So for the estimation of rainfall and for several other applications. So the advantage of KDP is actually the KDP is not affected by attenuation, since it is actually based on the phase measurement, so it is not affected by the attenuation. So whereas the backscatter power will get affected by the attenuation, but then KDP is not affected by the attenuation. And also if you are using a high frequency radars, the KDP generally increases with the decreasing radar wavelength. So if you are using a high frequency radar, then the KDP value will be very large. You will get a large KDP, so that will be very useful, because otherwise the differential phase is generally a noisy parameter. But then if you are using a high frequency radar, KDP becomes very, very important. So there are several other advantages with the KDP. That's why it is preferred for several applications. So when I say that what are the major advantages of polarimetric radar, then the three things comes into the mind. One is the improved rainfall estimation. So whatever problems we have seen with the single polarization radars, I think those problems we can overcome with the polarimetric radars. So we can improve the rainfall estimation. Then also we can understand the microphysical process occurring inside the cloud and below the cloud. So we can see on the right hand side, I have shown several microphysical processes actually which are responsible for the whatever rain we see at the ground. So starting from the condensation to collision coalescence process, breakup, evaporation, melting near the 0 degree isotherm level. Then in the ice phase also you have several things: vapor deposition. Then they grow due to the mainly due to the aggregation and then drying. So there are several processes, and then polarimetric parameters will give some indication that what kind of microphysical process is happening inside the cloud. Then we can also classify the hydrometeors, whether the hydrometeor is a hail, or is it a raindrop, or is it a big drop, or is it a snow. Like that we can also classify the hydrometeors using these polarimetric radars. um, so this is one example. At Gadanki, what we have a dual polarization radar at Gadanki, an expand dual polarization radar, and then we just compared the rainfall rate with the different relations using the KDP, using a JEDA relation or a multi-parameter relations. All those things we have used, and then we compared with the rain gauge measured um, rain rate, rain accumulation. And you can see the x-axis shows the time, y-axis the rainfall rate accumulation, and then the KDP relation actually is giving a very good result, KDP, and then some other relations. So since we have several parameters at our disposal for estimating the rainfall rate, then there is another puzzle comes, which one I should use to estimate the rainfall. So people have developed some tree based the decision tree based algorithms to actually to select which parameter we have to use the rainfall, particularly when the uh, generally people use the JEDA relation when the rain is very when you have a very light rain, because in a light rain generally the drop is spherical in nature, so you will not have any problem with the JEDA relation. Anyway, the drop is spherical, then you don't get any polarimetric products because it is spherical in nature, so you will get the same type of reflectivity for both horizontal and vertical polarization. Your JDR also will become one. So you can use JEDA relation, but if the major problem comes if the drop differs from its sphericity, so it becomes like a oblate, then the problem comes. So in such cases we can use either KDP relation or a multi-parameter relation. So we can use different things. So people have various algorithms are available, decision tree algorithms are available with different thresholds. We can for our region we can also develop our own decision tree algorithm. And then if you say if you think about the different microphysical processes, I'm just telling what is the microphysical process, and then how the polarimetric parameter will vary if that process happens. See, for example, the collision coalescence. Collision coalescence is actually if the drop collides with another drop, then they coalesce, and then the drop size will increase. Okay, so then the drop size increases, then what happens is the reflectivity ZH is actually is proportional to the drop size, sixth power of the drop size, and also the number concentration. So the obviously ZH, because the drop size is increasing because of the collision coalescence, the reflectivity also will increase as you come down. And then because the differential reflectivity, the drop size increases, it's a shape it differs from its sphericity, so it becomes like more like a oblate shape. So then the JDR will also increase, so then the KDP will also increase. So and then the opposite thing happens, particularly when a breakup occurs. If the drop is very big and if it breaks into two small drops, then the reflectivity decreases because of its dependence on the sixth power of the drop size. Because the part the size drop size are becoming smaller, so the differential reflectivity also will decrease, the KDP also will decrease. And if you see both collision coalescence and breakup happens, then at the surface you see this kind of a raindrop shape. if evaporation occurs, then what happens is the reflectivity will decrease as you come, if the drop comes down. Then the differential reflectivity generally is actually the evaporation um, is the effect of evaporation is more on the smaller drops, because smaller drops fall very slowly, so they spend more time in the atmosphere, so there is a good chance that smaller drops gets evaporated first. So the bigger drops will remain more or less same. They also bigger drops also gets evaporated because the outer surface area is very large, so there also some evaporation happens, but then the time they spend in the atmosphere is very less because of their size. They fall fast. So the differential reflectivity doesn't change much when evaporation occurs. Because of the smaller drops, concentration is reducing, then the KDP also will reduce. And then if you see that the surface, you will see this kind of shape, modified DSD shape due to the evaporation. And here the one picture we are showing here from this is the melting region, melting layer, radar broadband, and then as the rain shaft comes down, like you can see the decrease in the reflectivity due to the evaporation, but then you don't see any big change in the ZDR. Then the size sorting, particularly in this, is a very common phenomena, particularly in the convection. When you have a strong updraft, then this small updraft, the strong updraft will take away the smaller drops aloft, and whereas bigger drops, because of their own mass and velocity, they will fall down. So because of that, actually, only bigger drops will be able to come down. So then the reflectivity, because of the smaller drops are not there, reflectivity will decrease as you come down, because only bigger drops are only coming, the differential reflectivity will increase, and because the rain volume is also decreasing, the KDP also will decrease. And then this is showing some example the size of size sorting. Then clearly you can see here the differential reflectivity is increasing, whereas the reflectivity is decreasing as it comes down. Then this when the vapor deposition occurs, because vapor is depositing on the ice particles, so the size of the ice particle will increase. Once the size of the ice particle increases, then obviously the reflectivity, differential reflectivity, KD, all will increase. Whatever and then of course right hand side I'm showing different types of ice crystals present in the atmosphere, like plates, needles, then this snow, then other things. So then so what happens when a riming or accretion occurs? Actually, riming is actually nothing but actually supercooled water. When it collides with ice particle, it just sticks onto it, freezes onto it. So and then the size of the particle will increase. Generally, it occurs in convective systems. When the heavily rimed particle becomes a hailstone. So when this kind of thing happens, since the particle size is increasing, the reflectivity will decrease. The reflectivity will increase. Particle size is increasing. But what happens is to the differential reflectivity, because the hail will tumble, so it will appear like like a spherical shape. So the differential reflectivity will decrease, and then KDP will also decrease with particularly for the hail. So we can also identify the hail from the variation of reflectivity and differential reflectivity. So when melting happens, the ZH increases. Then similarly, the ZDR also increases. Then KDP also will increase, but the ρHV will decrease in the region of melting. That as we discussed earlier, because you will have both mixture of both water and ice there. So I'll just show one example here, what we have seen at Gadanki. So this is actually whatever I said that I have listed here. I think you can find this table in a Rijko and Zernik book. And then you can see these are they call polarimetric fingerprints, microphysical fingerprints of polarimetric variables. So you can see for size sorting happens, then reflectivity decreases, differential reflectivity increases, KDP decreases, ρHV doesn't change much. So like that, for each microphysical process, how the polarimetric variables are changing. That we can see from this table. We can guess actually what kind of microphysical process is happening inside the system. I'm just showing one example what we have seen at Gadanki. You can see there is a Nivar cyclone which came very close to the Gadanki, to the radar site. And then what we did is, there are so many convective storms, convective cells formed in the cyclonic environment, and then we tracked those convective cells and then just plotted here as a function of height and then time. And then we try to understand actually what is happening inside the convective cell. And we can clearly see here the reflectivity has reduced in the initial phase of the convective storm, and then the differential reflectivity has increased here. Then which like you can see here, this is the signature of the size sorting. So because it's the initial phase of the convective system, generally the updrafts will be very strong, and then you can get this kind of microphysical process predominantly. And then the upper heights you will have the rhyming process will be dominant in the mature phase and the initial phase in this region. And then you can see the differential reflectivity also reduced here in this region, but whereas the reflectivity is very large there. So which indicates actually some rhyming process is happening there. So like that, several microphysical processes within the convective cell during the several processes we can see that actually in the decaying stage, particularly here at the low level only we see the increase in the reflectivity, differential reflectivity. So then the indication of the collision coalescence process. So like that, several processes we can see in the when a convective cell develops, it matures and decays. All these things, all stages, what kind of microphysical process happens, that we can see very clearly with the polarimetric radar. The another application is actually raindrop size distribution. Raindrop size distribution is a fundamental property of rainfall. So we can, once we get it is nothing but the concentration of raindrops of the total number concentration of the raindrops per unit volume of air. So we can, but this information is required for several applications. Like if you want to understand the microphysics, we can see the variation in the raindrop size distribution. Also, we can infer the microphysics. Then we can to estimate the polarimetric rain estimators, then radio communication, soil erosion studies, then microwave remote sensing. For all these applications, there the information on raindrop size distribution is necessary. So then is it possible to derive or rectify raindrop size distribution with polarimetric radars? So yes, it is possible. So we will see that in a moment. Basically, once we get the raindrop size distribution, we can calculate several parameters. Initially, what I call it as moments of the raindrop size distribution. We can calculate how many total number of drops are there. Then just take these. You can add all the total number of drops of all drop sizes. You will get that per unit volume. Then you can also calculate the drop diameter, mean drop diameter. There is a first moment. It is a single geometric mean, but then that doesn't give a correct indication of the drop diameter. So people have estimated later, they have calculated the mass weighted mean diameter. It's actually the fourth. It is only the fourth moment ratio between the fourth moment and third moment. You can calculate the mass weighted mean diameter, so that will be more representative of the raindrop size distribution diameter of the raindrop size distribution. Then we can also calculate the optical extinction is the second moment. Then we can also calculate the total liquid water, how much liquid water is there inside the cloud, which is the third moment. Then we can also calculate the rainfall rate. Rainfall rate is nothing but the flux of the liquid water. So you have to multiply the liquid water with velocity. So you will get that. Then so we can call it as rainfall rate as a 3.67th moment of the raindrop size distribution. Then attenuation by precipitation, then kinetic energy, then radar reflectivity factor. These are the fourth, fifth, and sixth moments of the raindrop size distribution. So generally, raindrop size distribution, if you want to estimate, then their distributions are model, assumed to be follows a model. Like for example, initially that it is assumed that the DSD will follow the exponential distribution. So the exponential distribution is a 2-parameter model. The n0 and lambda, nd is equal to n naught exponential minus lambda d. Lambda is the slope of the DSD, and then n0 is the intercept parameter. So if you know n0 and lambda, you can get the raindrop size distribution. So how do we get n0 and lambda with the polarimetric parameters? So the lambda and dm are actually, if you are assuming DSD follows the exponential distribution, these are related. Lambda is equal to 4 by dm. And dm you can estimate from the ZER, because like I told you before, that ZER is a good indicator of the raindrop shape, and also we can use this information to calculate the mass weighted mean diameter. So we can calculate, if you know A and B coefficients, we can derive empirically, and then ZER we can use we can get the polarimetric radar, and then ZER can be converted into dm, and from the dm we can calculate lambda, and not also we can calculate using this relation. So but then we need to calculate these coefficients A, B in this relation as well as in this relation, that we can calculate typically either from the literature we can take, or from the for that region. If you have a densitometer, we can calculate we can calculate all these parameters, and we can get the relations between them. So this is what we did at Gadanki. And also, if you're assuming that raindrop size distribution is following a gamma distribution, then gamma distribution is a 3-parameter model. So you need n0, mu, and lambda. So it follows like that. So the mu is the shape parameter, this additional parameter. So the value of mu, whether it is a positive, negative, or whether it is 0, so that decides whether the shape of the shape of the distribution. So if mu is less than 0, then it will look like the concave shape. The distribution will look like this. That means the number of smaller drops will be very high compared to very high. When mu becomes 0, the gamma distribution becomes exponential distribution. So if you substitute 0 here, it will become d power 0. It is become 1, and then it will become like exponential distribution. If mu is greater than 0, it will become like a convex shape distribution. The number of smaller drops are small compared to the mu less than 0. So the shape factor decides what type of shape the distribution is having. And then since it's a 3-parameter model, you need 3 independent radar parameters to calculate 3 parameters, but radar doesn't provide 3 independent parameters. So what people proposed is, actually they found a relation between mu and lambda. So using this relation, and then the 2 parameters, two independent parameters, we can calculate all 3 parameters of gamma distribution using the radars. And also some people assume that distribution is follows log normal distribution, and some people use modified gamma distribution, and some people propose the beta method. So there are various methods people have proposed. So then if you use all, and then these parameters, you can calculate all these parameters for those distributions using the polarimetric radar parameters. You can calculate all these parameters. So this is how we did for one example I am showing, and then we have calculated both dm as well as the n0 and t, all these parameters, and then more details can be found in this paper. Then coming to the hydrometeor classification. So we suppose if you want to know what type of hydrometeor it is, whether it is a rain, or is it a hail, or is it ice crystal, dry snow, wet snow, all these things. A simple Boolean type of classification is not possible, because you see here rain for reflectivity for rain is between 5 and 50 dBz. The same range you will see several other parameters also are giving same reflectivity in the same range. Similarly, other parameters also. So there is a overlap of these parameters for each hydrometeor. For example, one example is shown here. these between the data, this is between the ZDR and Z, and you see the rain will give this kind of two, these are the two thresholds for the rain. But there are so many other hydrometeors which are giving which are falling in this range. So so we don't know whether it is rain or it's a dry snow or is it a wet snow. So it is very difficult to identify the hydrometeor from one parameters or two parameters. So because of the overlap of these parameters. So people have used different types of classification, hydrometer classification scheme. First, initially they started with the decision tree type of classification, because the decision tree classification failed mainly because of the overlap of different parameters. So then some statistical decision theory people have proposed. But this is kind of an optimizing the decision tree. It reaches some, it has produced some kind of a optimum values, but then still it's not perfect. So then later people have started neural networks. But neural networks, because if you want to train any neural network or any artificial machine learning technique, so you need the reference data. So based on the reference data, you can train the model, and then you can get you can develop the technique. But we don't have those many data sets, so it requires a lot of data, reference data. But then that kind of reference data is not available, so it is very difficult to develop the neural networks. Also, people have, I think, people have mostly follow the fuzzy logic schemes for classifying the hydrometeors. Fuzzy logic scheme is a very successful scheme, and then many people have developed several fuzzy logic schemes. So these are some of one or two examples I'm showing here. The CSU led by Professor Chandra, they have developed a scheme, and also they have taken measurements in an aircraft. They have taken aircraft measurements, and then they compared their algorithms with the reference data that they got from the aircraft, and then it was very successful. And also these are all operational algorithms by Japanese group. So people have developed their own algorithms by varying the thresholds, and then develop these classification schemes. So I'll skip this. So what is that there in the future? Then if you see that whether it's a single polarization radar or dual polarization radar, mostly they use mechanical servos and then this system. So they will take a lot of time to complete one volume scan. So typically, depending on the number of elevations they use, they take anywhere between 8 to 15 minutes to complete a volume scan. But there are several rapidly evolving systems, like very thunderstorms, and the lifetime of the thunderstorm sometimes can be half an hour or maybe less than that. So in those kind of cases, you hardly get only 1 point or 2 points. And then, for example, the cloud burst. Otherwise, cloud burst will give a lot of rain, but then you hardly get 1 or 2 points if you are going with the traditional volume scan. So that's why the people are now developing electronic scanning Doppler weather radar. So the phased array weather radars they're developing. So they have several advantages over the traditional conventional radars. So some of the advantages, actually, you can get the rainfall you can complete the scan within few seconds. So and then also we can also develop, because there's many of them are having multiple receivers, so you can image the total the cloud system, and then also the digital beam formation you can use to get the echoes from the different regions at the same time. So there are several advantages with this kind of Doppler weather radars. So I think mostly people are now moving from the conventional scanning weather radars to E-scan Doppler weather radars. So this slide I borrowed from Toshiba. So you can see how the evolution of a weather radar happened from 1950s to 2020 or much later. So in the normal analog radar, then the estimation of rainfall and then augmented by the Doppler capability, then the dual polarization capability. Then now everybody is moving towards the electrically steered phased array radars, and then the technology also, if you see, then from the initial magneton based systems, now people are talking about the solid state systems. So the technology has also have evolved, and also the type of radars are also evolved. And then there are of course some challenges. Now the one challenge is how to developing a phased array radar for our applications. Then still there are another big challenge is actually people now are working on that is with a single polarization radar you are getting reflectivity and velocity, Doppler velocity, and then many modelers have actually assimilated or they have developed several schemes to assimilate these data sets. But polarimetric radar provides a lot of information, but then still I think modelers have not utilized it completely, because several parameters, how to make use of these parameters. So far what they did is only they only use the polarimetric products to validate the schemes and other things, but then they have not really used the data for assimilation and other things. So we need to find out how to better utilize the polarimetric radar data for modeling. Thank you. Thank you very much for your patience listening.
Thank you,
I
sir.
think I have completed within my time, I think. Okay.
Yes, sir. Yes, sir. Well ahead of the time. Okay, now we will have a photo session. So please stop sharing the screen. Narayana Rao, sir, please switch on your camera.
I think I'm little away from my Wi-Fi, because somebody else was sitting there, so maybe it is video is not coming here. That's why I'm using already.
Okay, it's okay. Okay. So I will take this one. Pradhan sir is there. Okay, I have taken with whoever available. I will take. Okay, then we will move to the Q&A session. I invite Dr. Divya Prakash for handling the Q&A session.
Thank you, sir, for this opportunity. Actually, in question answer session, I am not able to see any question, but on YouTube there is one question. So I am just taking that question. So there is one question. Is it possible to segment the agricultural area using the Sentinel-1 dual polarization features?
Pardon, I could not understand the question. Can you repeat the question?
Yeah. Is it possible to segment the agricultural area using the Sentinel-1 dual polarization features?
He's talking about the spaceborne radar.
I think so. Yeah, because
I think that is a spaceborne radar, Sentinel.
Yeah, Sentinel.
She is asking from satellite radar images.
Yeah, satellite radar images, actually that is a different thing. But anyway, with this radar, it is not possible. Yeah, this is what we are talking is a Doppler weather radar.
And another question is how we can minimize errors and as well maintain data quality from practical point of view, and its application or use for research purpose.
Yeah, this is what exactly I told. Actually, from the operational point of view, what we need is we need a good rainfall estimation. So, and then polarimetric radars actually overcome several problems that we face with a single polarization radar, and so it will give a better rainfall estimation. So, from the operational point of view, we can say that it provides a better rainfall estimation. And then for research point of view, it provides several it is having several applications, like it gives the information about the microphysics, what kind of microphysical processes are occurring. Just by looking at the variation of these polarimetric parameters, we can infer the microphysics, what kind of process is happening. And also we can derive raindrop size distribution, and also we can uh, identify the type of hydrometeor present in the atmosphere, I mean present in the cloud, what type of hydrometeor it is, whether it is a hail or is it a non-meteorological, even non-meteorological targets also we can identify. So all these things we can lot of information we can get from the research point of view.
Thank you, sir. So no more question answer session. Thank you.
Thank you, Dr. Divya Prakash, for handling the Q&A session. Now I invite Aditya sir for some concluding remarks. Aditya sir, are you there?
Okay. Thank you, Rakesh, and once again, thanks to Dr. Narayana Rao for his lecture, and he covered the advanced features of the polar dual pole radars and its application both operational and research. So I'm sure this is going to be great help to those students who want to take up advanced work in radar meteorology and its application. And as it is going to be available on YouTube, I think the students who could not attend this lecture will also be benefited. So thanks once again to Dr. Narayana Rao for his lecture.
Okay. Pradhan sir, are you there? Sir, please give some concluding remarks.
To me?
Yes,
You're
sir,
talking to me?
Yeah,
please
Pradhan
give some
Sahab,
concluding remarks.
you can give your specialist remarks.
Okay, okay, sir. Sir, I was not well, so I could not listen properly. So, Dr. Narayana Rao, sir, we are grateful to you for sparing your valuable time and delivering this excellent lecture. I was listening. As I said, I'm not well, suffering from dengue. So I was not sitting, but I was lying on the bed and I was listening each and every word of your lecture. Very educative, and what differentiation you have made between the single polarization and dual polarization, it was remarkable. So I feel that all the participating members and from the different countries, they are getting benefited from this lecture now. So I feel that they should revise each and every lecture, whatever we have done so far, and it will be highly valuable for each one of you, as radar meteorology is one of the latest things available in the nowcast. So at the end of this lecture now, once again, I am grateful to Dr. T. Narayana Rao, Professor Aditya sir, Mohan Dasi, and all other members of the Sama team. Not many things from my side. Thank you very much.
Thank you, Pradhan sir.
Uh,
Now it's a time for vote of thanks. Sir?
Just a minute. Let me thank Dr. Pradhan, that who is down with the dengue still. He agreed to our request on short notice, and also giving this concluding remarks. Thank you. Please take care. Get well soon. We wish you a speedy recovery. Thank you, Dr. Pradhan.
Okay, so now we will have the vote of thanks. I invite Dr. Srikala PP for delivering the vote of thanks.
Is it visible?
Yes, yes.
Good
You
afternoon.
can make it, you can make it full screen.
Yeah.
Good
It's
afternoon.
up. It's up.
I feel honored and privileged to have the opportunity to propose the vote of thanks for the lecture 18 of online course on radar meteorology organized by SAMA and ACARR CUSAT on behalf of everyone present today. First and foremost, I would like to express my deepest gratitude to Dr. Devendra Pradhan, Chairman, Advisory Panel of SAMA, for delivering warm welcome address and setting the perfect tone of this event. A sincere thank you to AVM retired Professor Ajit Tyagi sir, President of SAMA, for his thoughtful address highlighting the significance of our gathering and the ongoing initiatives of the organization. We are truly grateful to Dr. T. Narayana Rao, Scientist SG at NARL, Tirupati, for sharing his valuable insights on Introduction to Dual Polarization Radar, Inferring Microphysics from Polarimetric Parameters. Your knowledge has certainly broadened our understanding, and I am sure it will inspire further research and collaboration in this field. I also extend a heartfelt thanks to Dr. Divya Prakash for moderating this session and for ensuring the interactions were meaningful and engaging. Thank you to Dr. Rajesh Pees for smoothly moderating the session and keeping the proceedings organized and on the track. Finally, I would like to thank you, all of you, the organizers of the program, our esteemed audience, experts, and participants, for your valuable presence and insightful questions. Without your engagement, this session would not have been enriching. Once again, a heartfelt thank you to everyone for contributing to the success of this program. We look forward to continue learning and collaboration. Thank you.
Thank you, Srigala. Now we will wind up the session. Thank you all for attending the online course.
Thank you.
Yes, yes. Thank you.